1, let me go to table 1. This is table 2. Okay, table 1 is this. Table 2. All right, let's use this table. Let's start with this. What do you see here in terms of the reporting of the N and N? Remember that this is the context that this is complex survey data. Can somebody take this product, these numbers here, 582 divided by 569, and can somebody verify whether or not they get this number? That's the first lesson of the day. When you divide 582 by 5659, what do you get? And it doesn't have to be this number. It can be any number here you see at all. Do we have any answers? Can you guys hear me at all?
We can hear you, Prof.
Okay.
We have 0.10.
Okay. All right, you have to multiply by 100. Okay. So I can also pull my own calculator. Since you guys are being shy.
No, the answers are now slowly coming.
Okay, all right. Oh, awesome, great. So if you pick any random column here and you calculate the number, the probability is very high you're not going to get this percentage here, right? So for example, let me just pick a random one here. 122 divided by 872, 122 divided by 872, 872. The answer is 13.99. But the answer here is 18.2. Does anyone want to explain to us what's going on here? What in the world is happening? Why aren't the numbers matching up? I don't want to show the author's name because I don't want to focus on the people who wrote the manuscript. I want to focus more on the results and what we can learn from it. All right, so let's get back to the topic. Why aren't the numbers matching up? And what lessons can we draw from that when we are analyzing and reporting data from complex survey data? Any volunteers?
Feel free to raise your hand if you want to speak. Someone says weights. Total numbers of males and females is not adding up.
Okay. Yeah, but I would like someone to speak up and explain. And what's the moral of the story? So we want to draw an observation, which we're drawing, but more importantly, what's the moral of the story? No, what we're saying is they take the column here, for those who are confused, we're saying that before we dive into writing manuscripts, we want to draw a lesson from manuscripts that have already been written. We're using complex survey data, so it makes sense that we should draw some lessons. It's easier to look at what other people have done and learn from that than just repeat the same mistake they made, right? And we said the first lesson is to look at this column. Here they've reported n over n. Small n typically is referring to the numerator of analysis, while the n, the large n, refers to the denominator. So what we're saying is take any random numerator here and divide by the denominator. Ideally, you should get the same number here, but we're saying that the chances are very high that what you will get won't be what is here. And we already demonstrated that. We looked at this number, we took a random number here, which was 122 divided by 872, this number. We divided it, we got from our calculation, the result is 13.99. The result here was 18.2. The question is why? Why don't the numbers match up? That's the first question. And number two, what lesson can we learn from that in terms of what to do or what not to do when using complex surveys. I promise you, this is not a trick question. Yesterday's class was hard, so I will not make today's class easy. No, no takers? Oh, no,
Missing values.
no. Somebody gave a correct answer earlier. They referred to weights. Do you want to explain more?
Buddha.
So, okay, the problem is weights, right? The way we think of data analysis with random samples or self-weighted sample is not the same thing when we're using weighted samples. When you're using unweighted samples, of course, these numbers will match up. However, when we're using unweighted samples, remember that the math is not so, it's a bit different. Here is what happens when we use unweighted samples. Let's say we're looking at prevalence of tobacco use and we have, let's say an individual here said my 0, I'm not a tobacco user. The guy on row number 2 says I'm a user, I'm not a user. When we look at the unweighted analysis, right, the prevalence is just simply the mean of this. We got to the average, right? Where we are simply taking the average of all of this. That's what your software is doing behind the background. It's simply taking an average, which is the same thing as saying that we have this. Remember, this is tobacco use, and this is the weight. This is the same thing as saying everybody has a weight of 1, right? An unweighted analysis is the same as saying a weighted analysis where everybody has a weight of 1. In which case, the mean here will be the same as saying this is equal to 0 times 1 plus 1 times 1 plus 1 times 1 plus 0 times 1, right? Then all divided by the sum of the weight. 1, 2, 3, 4. So divided by 2 divided by 4, 0.5. So when you're doing an unweighted analysis, that's what's happening, right? It's either you're just taking an average of this, or you are having a scenario where you have this, let's just put it in one simple equation, divided by sum of all the weights, right? So that's what the software does in the background. And that's why when you have an unweighted scenario, this division will always add up to this. However, when you have weights, it's different. When you have weights, what we're having is this. Instead of everybody having a weight of 1, obviously in weighted analysis, the weights are different. This guy may have a weight of 5. The next guy may have a weight of 6. This may have a weight of 2. So obviously, the numbers will not match up. So what's the moral of the story then? Who can draw the moral of the story from what we just described? So the moral of the story is that when we are doing weighted analysis, what don't we want to do? What don't we want to present? Any takers? Well, suddenly, why are we so quiet this morning? Okay, let me put it a very simple way then. When we're presenting data from complex survey analysis, do we or do we not want to show this column, n over n column? Now I've reduced the binary choice. Exactly. That is very smart. No, we don't, right? So rule number 1, when presenting data from complex surveys, you do not want to show a column like this saying n over n, right? Because it does not add up. Now you're leaving the users very confused. And again, remember that once you do analysis with complex survey data, the emphasis has shifted from you're no longer interested in the 5,659 individuals who participated in the survey. You are interested in the entire population. So imagine that this was a survey of youth aged 13 to 15 years old, right? And you were saying that, let's pick an estimate, for example. This is the prevalence of, let's say this is the percentage of those who used tobacco use, right? If you're going to report that result in an unweighted sample, you would say 9.9% of study participants, or 9.9% of the 5,659 participants used tobacco. That's how you're going to say it if the analysis were unweighted. But now that we're weighting the data, how will you say it? What would be the correct way to say it? Remember, this is our weighted analysis. The participants are drawn so that they're supposed to be representative of all of Ghana, right? They're supposed to be representative of 13 to 15-year-olds in Ghana. We've applied weight. And remember, we said that if it were unweighted, we would say that 9.9% of study participants, emphasis on the word study participants. But now that we've weighted the data, that would obviously not be correct. What would be the correct thing to say? Any thoughts? Remember the cycle of inference, right? Where we're taking a sample and making inference to the broader population. The broader population is all 13 to 15-year-olds in Ghana, right? So once we've weighted the analysis, we have stopped talking. We're no longer interested in the sample at this point. The sample is dead to us. So instead of, we will say 9.9% of all 13 to 15-year-olds in the Ghanaian population. No longer no longer the sample of 5,659 people. We don't care about that sample anymore, right? We're interested in the general population now. So that's something we want to pay note to. So when you are reading the results from the findings, you don't want to make any references about, study participants should not be appearing in your results. So let's see, for example, how these individuals wrote their results. Let's see. Okay. I'm trying to find a part of a result. Okay. All right. They did not necessarily, use any language in either direction. But anyway, the moral of the story is that don't show n over n like this. And when you're describing your results, you must make sure you describe them in terms of the overall population, very importantly. Next, let's look at the presenting of the results. When you're presenting results from complex survey data, you want to make sure that, and in general, any result at all, you want to make sure that your study is not a p-value study, right? So look at these results here, for example. Among all respondents, age, P equals this, amount of pocket money, P is this, exposure to secondhand smoke at home, were significantly associated with tobacco use, right? And it continues. You can see a whole bunch of p-values. What's the problem with this? You can see a lot of p-values, but what are you not seeing? As analysts, we're all analysts here, right? Wherever you see a p-value, you're supposed to see what else? Okay, a p-value tells us what? What's the p-value telling us? p-value is an answer, right? But it's an answer to what question? Let's start from there, right? I think we can all agree that it would be quite bizarre for you to provide an answer to a question that was not raised. Imagine somebody just raised their hand and said, the answer is 20. The question will be the answer to what question? Like, so a p-value is an answer, but an answer to what question? No, I want in simple lay terms, right? When we say here, for example, this sentence, for example, among all respondents, age was significantly associated with tobacco use. So the answer they're giving here is age was significantly associated with tobacco use. But that's the answer. An answer, but what's the question? So can somebody just raise up their hand and explain? Yeah, Ify.
So I think it's always that, with the p-value, we're trying to say if there is a difference, right? Like if there is a difference between the parameter in the sample versus the general population. So
Okay.
go ahead.
Yeah, so I'm going to take the word there, the difference. So we're asking, is there a difference? Right? Is there a difference? Imagine you have two people standing, they, let's say a boy and a girl, and you're like, oh, there's a difference in the height. That's not interesting, right? Or if you're, for those of us who watch soccer, you say, oh, they match, one side won, right? That's like a p-value. That's not interesting. The question is, how many goals did each side score? It's the declaration that one side won or one side lost is only interesting when you've told us the number of goals scored by each side. When you provide p-values without any other thing, it's like I said I'm thirsty and you hand me a cup, but the cup is empty. Like, what am I supposed? The cup is only meaningful if there is content inside the cup. The cup in of itself is interesting, but I mean, as a thirsty person, I want to have some water in the cup. So giving me a p-value only is like handing me a cup without any water in it. So the question is, what will be the water in the cup that will make it complete?
The confidence interval.
Try again. In general, you can use p-values or confidence intervals, right? So here they've chosen to use p-values. So that's like giving me the cup. What do I expect to be inside the cup for me to say, all right, this makes sense? Because right now it's not making any sense at all.
Can I try, Prof?
Yes, please go ahead.
Okay, effect size.
Exactly. The effect size. Can you please simplify that so that all of us can understand? What do you mean by effect size? Yes, Kenneth.
Okay, is the effect size is what tells us the magnitude?
So what are examples of effect size? What are some of examples of things that could be inside this cup? Because inside my cup, I could have water, I could have liquor, I could have wine, and all of those things are drinks, right? What are the different drinks that could be in this our statistical cup that would make sense when we pair with a p-value? Because we don't want an empty cup for sure. So, and it can be in any one of many things, right? So what could it be? Yes, I see somebody say prevalence. That's correct. So in this case, you could say the percentage of smokers among males was 50%, among females was 20%. And so the p-value was this, right? Now you have given me a cup, and importantly, you've put water in the cup. The water in the cup could also be odds ratios. You could say an odds ratio of this, and the p-value is this, or the confidence interval is this. It could be relative risk, it could be means, right? The mean of this was this, and the mean in that group was that. But never ever should you just present just p-values like this. This is completely incoherent, right? It makes no sense. So please let us not do this. This is bad practice, right? wherever you have a p-value is answering the question, is it different? But you have to provide us context, right? You have to provide the water in the cup along with the cup, not just give us an empty cup, right? So that's one of the things we want to avoid. We want to make sure that we are providing p-values alongside with the effect size that we're measuring, right? All right, now let's look at some other things that we want to avoid. Let's look at another, oops, I don't want you guys to see the names of authors because the focus is more on the results and what we want to avoid. Now, this shows table 1 characteristics of Senegalese student participants, also from a global youth tobacco survey. Now, they are just showing the percentage or the composition of the population by these characteristics. When we are reporting, what do you see is wrong here? They are saying 45.7% were boys, and the confidence interval was 40.9 to 50.5. And they're saying 54.3% were girls. What's wrong with the presentation here? All right, let's frame it this way now. We only show confidence intervals when we're capturing estimates, right? These aren't estimates, okay? When you're describing the composition of a population, that's not an estimate. You're just, estimates include things like means and prevalence, right? So the moral of the story here is that when you're just showing what the population composition was, where you expect all of these things to add up to 100, you don't show confidence intervals, right? You just report the percentages only without any confidence intervals. So please, when you're describing and typically this is the table 1 usually. So your table 1s should not have confidence intervals because they're not point estimates. There's no population parameter for that. You're just trying to describe the population overall, right? So that's the lesson we want to learn from this. Okay, now let's move on to the next lesson that we can learn. All right, we've already said on day 1 that we should collectively united in our hatred for pie charts, right? We don't want to use pie charts in general, of course, in general, because they're quite hard to make relative differences. So please try to avoid this, right? Let's develop a collective hatred for them. All right, then let's move on to the next element here. Now, here, in general, when you talk about a column, whether it's a column in your data set or a column anywhere, a fundamental principle of capturing data in a column is that one column should only capture one thing, right? Don't try to capture many things in one column. Do you see that rule violated here? If so, how? And what lesson do we want to draw from there? All right. Does anybody want to take a shot? What?
Yes, Prof.
Okay, go ahead, please. Yes.
Okay. The rule that has been violated, one is the p-value. When you look at the column of characteristics, there's a p-value below it.
Exactly. So if you set characteristics, I don't expect to see p-value, right? No, that just present the characteristics. I mean, you are at liberty as a researcher to choose how you want to show your results, but you should not start with the wrong ways. There are so many ways you could present that same information, right? So generally, try to avoid one column should capture only one thing only and nothing else. So you can easily create a column for p-values and say p-value here, and then we can interpret it, right? So please, in general, do not show many things in one column. One column, one item. One column, one item. When you look at the p-values and you compare the point estimates, In girls, the prevalence of ever use of shisha is 6.9%. The confidence intervals are 5.1 to 9.3. The prevalence among boys is 13.2. The confidence intervals are 10.4 to 16.6. First of all, what do these confidence intervals mean? Oh, someone is asking, this is research. This is actual published work and research work. I just grabbed some random ones just so that we can walk through them. So yes, they are actual publications. So what do this confidence, how do you interpret them? So let's look at it from two scenarios. How do you interpret them to a fellow scientist, and how do you interpret them to a policymaker? Let's start with the easy one, the policymaker. How will you interpret these results to policymakers using confidence? Yes, go ahead.
Maybe, Professor, I want to give a trial. Actually, when you are choosing the confidence interval, like for instance, this one is 95. So if you see those statistics for the girls and the boys, all lies between the confidence interval, that is 95. So that one, normally in statistics, you normally say that one it is those different, like they are significant, and that one confirmed to the p-value itself, it is significant. But then we can say that since those characteristics lie between the 95 CI, so we can of course presume that there is a statistical significance. The findings are statistically significant in the first case.
Okay, thank you very much. Okay, let's focus on this, right? Can you tell from the confidence interval for boys? I mean, what does this tell you? Like, what do you interpret from this estimate confidence interval? What are you looking for exactly here?
Okay, Prof, let me try.
Yes, please go ahead.
Okay, for this confidence interval, what we're looking for in terms of, suppose this study was to be done in another population, where will the confidence interval for boys lie? It will lie between 10.4 and 15.6%. Then also it shows whether it's wide or it's a narrow confidence interval. Thank you.
Okay, thank you. That's one thing we're looking for, right? We're looking for whether it's wide or whether it's narrow. And how do we know whether it's wide or narrow? Like, when you look at the confidence interval, what makes you know whether it's wide or narrow?
If it falls inside that confidence interval or outside that range.
If it falls within what?
That range, given the predetermined range, like this one now computed 10.4 and 16.6. Then the other way, maybe it falls outside the range now you got. I think that's what I can say.
Okay, but what are you comparing it against? What are you comparing it against?
Can I say something, Prof?
Yes, please go ahead.
My own opinion is that if the estimate is actually closer to the lower band than the upper band, that means it is narrow. But if it is far, that means it is wide.
Okay. Alrighty. Any other thoughts? Okay. All of us should have NCHS suppression rules. This should be something you should have. This should be a resource that everybody should have, right? You should have access to this. Let me drop a link for you, because we use this guidance from NCHS in a lot of things, including, for example, determining which estimates to suppress and so on and so forth, right? So let's go to this summary chart here. All right. Now, I'm giving you the example. The answer is right here, right? What threshold do we use to determine whether the confidence intervals are wide? Unacceptably wide. hints. This is the guidance I'm referring to. So what does this mean? Absolute value of CI width. What is it talking about? So you can choose to use one of two parameters, two guidances here. You can look at the absolute value of the width, or you can choose you look at the relative CI width. So absolute width or relative width, right? Let's go back to our estimate here. Where is it? Okay. What is the absolute width here? Can somebody calculate that number and give it to us? How do we calculate Go ahead, please.
Is it 6.2? Because you take the upper minus the lower bound.
Exactly. So 16.6.
Yes.
So the answer here is 16.6. How do I clear this?
Subtract 10.14.
Exactly. So 16.6 minus 10.1.
It is 10.4. 10.4. No,
right?
it should be 10.4. 10. Is it 10.4?
Oh, okay. All right. You're right. Okay. Okay, let me do it correctly. 16.6 minus 10.4. 16.6 minus 10.4. All right. The answer is 6.2, right? Now, when we compare to that benchmark, the benchmark says, is the absolute value of the CI width greater than or equal to 0.3? Now, we have gotten our answer as 6.2. Now, I want somebody to look at this answer against this benchmark and tell us whether our confidence intervals are wide based on NCHS standards.
I think it is wide because 6.2 actually is greater than 0.3 because 0.3 is a bit smaller than compared to what we got. So I would say it is a bigger.
Okay, 0.3, what is it? What is this number? Is this a proportion or is this a percentage?
I presume it is a percentage.
If it's a percentage, what will you see beside it? If it's a percentage, what sign will you see beside it? We always use a particular sign when we're referring to percentages. What sign is it called?
Hello, Prof.
Yes, go ahead. Okay, we can't hear you. I think the line is breaking. Okay, so this is not saying 0.3 as a percentage. This is a proportion. So in other words, this is, if we were to convert this to percentage, what's the answer?
%30%.
30%, exactly. So NCHS is saying that when you subtract the upper limit and the lower limit from each other, the difference should be less than 30%. Well, we did our subtraction and the answer was what?
6.2.
Exactly. So it's 6.2. So what's your conclusion? We need to be able to draw inferences from our work, right? So what's the inference from here?
Prof, in terms of percentage, is that what you're asking? That means if we're going to have 6.2 in terms of percentage, that means 62, right?
No, we're saying no. This is already in percentage points. We subtracted 16 percentage from 10.4 percentage from 16.6 percentage, right? And the answer is 6.2 percentage points. NCHS guideline says that your confidence intervals are deemed to be too wide if the percentage point is 30 percentage points or more. So on one hand, the standard says 30 percentage points, but we had 6.2 percentage points.
It is less.
Exactly. 6.2 percentage
less.
points is smaller than 30 percentage points. So that means that our confidence intervals are fine. See,
It's narrow.
yeah, it's, you know, we
It's
can't,
narrow.
but we can't say it's too wide. We can't say it's you know, unreliable, right? So the point is that we have to learn how to use benchmarks, and we're not the ones creating our own benchmarks, right? We use established standards to make determinations that say this is fine or this is not fine, right? We don't just pull the numbers from our reasoning, right? So let's go back to our data. So the confidence intervals here are fine. Now, are we looking at a null value here? Are we looking at a value of, let's say, 1 and saying that this number is significant? Like this 13.2, confidence intervals of 10.4 to 16.6. Are we determining significance by looking at this confidence intervals? And by the way, that is a trick question. Who wants to answer?
Maybe, Prof. I would say because when you choose that 95%, you presume that maybe the estimate should lie between that. You should maintain that. But then maybe by chance it's gonna be outside that range. But then you cannot just make an inference using only the upper and the lower bound. Perhaps you should have also the p-value, which you got here. It is significant. So I would say you should say the 95, but of course, not forgetting the p-value. I would say that.
All right, thank you. So the point I'm trying to emphasize is that when we're dealing with prevalence estimates or means, it's quite different from when we're dealing with odds ratios. If you have an odds ratio, for example, let's see if there's an odds ratio in this table. So here they have odds ratios. Here, we can look at this number and we can say, oh, this odds ratios does not contain the null value, which is 1. And we can say, oh, okay, this means that this result is significant. It's significantly different from the benchmark or the reference group. And we were able to do all of that by just looking at this single number. 2.05, confidence interval 1.53 to 2.73. We just looked at the confidence interval alone. I would say, okay, does this confidence interval include 1 or not? I would say, okay, it does not include 1 because it starts from 1.53 and then 2.73, right? It clearly does not include the null value. So just by looking at this, we were able to say that this result is significant. This is when we're referring to measures of association like odds ratios or relative risk. We can do that with those things. However, when it comes to descriptive statistics, we cannot do that. I cannot emphasize that enough. So you cannot come here and say, well, the prevalence among boys is 13.2. The confidence intervals range from 10.4 to 16.6. These confidence intervals do not contain 1. So this result is significant. That makes no sense whatsoever. Because this is descriptive statistics, right? So you cannot apply that same reasoning we just did with odds ratios here because these are simple. This number by itself is a univariate estimate. You know, remember we talked about univariate statistics, bivariate, and multivariable. This is just saying among boys, the prevalence is 13.2. What are you comparing with? There's no comparison being made. A p-value means we're comparing something. Remember? Here, this is just saying among boys, prevalence is 13.2. No comparison is being made, period. So it's ridiculous for you to say, oh, well, this means that since there's no 1 in this interval, it is significant. No, that makes no sense. So the moral of the story is that the way we make inferences from confidence intervals when we are referring to measures of association is extremely different from when it's just descriptive statistics like means or prevalences, right? The only functionality that confidence intervals serve in this case is simply to tell us whether the estimates are precise or not precise. And we use the NCHS guidelines to say whether the estimates are precise or not precise. I hope that is very clear. So now, sometimes you can look at the question we're asking here now in this case is the prevalence of ever use of shisha among girls significantly different from that of boys. Now, a trick we use in the field is we use overlap of the intervals. We sometimes check whether the prevalence estimates, whether the confidence intervals overlap to make an inference as to whether the results are significantly different or not. Now, here, do these intervals overlap? Yes or no? The intervals for boys and the interval for girls, do they overlap?
No.
No.
Why? Why do you say so?
Yes, they overlap.
Oh, you've changed your story? Okay,
No,
how?
no, no.
I
I just
said no.
because the interval of the girls is contained in the boys.
Do you care to explain how it's contained in the boys?
Yes, because the girls their interval can be found in the no, sorry.
No.
Prof,
No.
Okay.
Prof,
Okay, good.
if I would say,
Mm-hmm.
I would say they don't overlap because the same the estimates for girls or lies between our boundary, and of course for the boys still lies between the boundary. So I would say there is no overlap. Overlap maybe can come in if you could get one of them lying outside or maybe within the range. Like I would say that from my thoughts.
Okay, I want to really be convinced that we are all saying the same thing, right? Can somebody just explicitly tell us why they don't overlap based on the numbers we're seeing on the screen?
I don't understand now, but I'll pick up
Okay. This is becoming a disco hall. Alrighty. It became a disco hall really quick. All right. Yes, Maureen.
Okay, why I feel it did the confidence interval doesn't overlap is because that of the girls ranges from 5.1 to 9.3. And after that, there's still a difference, like you have 9.4, 9.5, 9.6, 9.7. Before you even get to 10, then the boy starts from 10.4 to 16.6. So it's actually there's a lot of space between the two.
Excellent. So that's very, very good. Now, let's establish a basic fundamental rule. Whenever the confidence intervals do not overlap, we can conclude with a great deal of certainty that the results are different. True or false? So whenever there's no overlap, all right, are there any falses here? If you reject that assertion, can you raise up your hand? Again, the statement here was whenever the confidence intervals do not overlap, it always means the results are significantly different from each other. True or false? Okay, I'm waiting for the one person.
It is true. It is true because they are significant. I would say that.
Okay. No, and don't ignore the p-value you're seeing here, right? Just pretend the p-values are not here. We're just trying to establish basic principles, right? So don't worry about the answer that you're seeing here. We're just thinking broadly in terms of principles. All right. Let's look at the opposite argument then. Whenever the confidence intervals overlap, it means the results are not significantly different from each other. If there's overlap, it means they are not significantly different. What do you say to that? Is it true or false?
True.
Okay. Any other answer? So on one hand, we said if there's no overlap, yes, it means they're always significantly different. On the other hand, if there's overlap, what does it mean? All right, let me give you an answer, right? Let's change the options. Instead of just true or false, the options you have to select from are true, false, or maybe. Exactly, the answer is maybe. So if there's an overlap, you can't tell just by looking at it, right? And that's where you need to do statistical testing, right? That's why we have formal statistical testing. We call this kind of tests the test where we just look at the confidence intervals and make a determination. What do we call this kind of test? We call them eyeball tests. But you're just using your eyeballs to check Okay, I see that this does not overlap. So we call them eyeball tests, right? They are informal tests. But you particularly need to do testing when there's an overlap, because then you're not sure. You can't just say anyhow. All right, so that's the moral of the story from there. Now let's see the next thing here. Let's come here. So one thing you see here, you have 3 stars, 2 stars, 1 star, and then you have, I'm sure there's a footnote here. This is P less than 0.05, P less than 0.001, and so on and so forth. Is this a good or bad idea? What are the authors, what could be interpreted from this? When you see this, right? Imagine you've never read any scientific paper before in your life, and you see this gradation: 1 star, 2 star, 3 star. Generally, where else do you see stars? Like in what other context do you see stars?
Okay, Prof. From my understanding and the way I've been doing, anytime you provide this, even if you run this analysis in SPSS, it normally gives you asterisk. Asterisk means those findings are statistically significant. But if you get, for example, most of the time, even in econometrics, the asterisks in those p-values indicate statistical significance values.
All right, thank you. But in what context? Let's leave statistics, right? In what other context do you see stars? And how do we interpret stars in general?
Like rating, like
okay,
how you
rate something. Okay, like rating of what? Let's be specific.
Rating in military like a military environment. Stars, 2-star general, 3-star, and so on like that.
Okay. But what's even more commonly, don't they rate hotels like 1-star restaurant?
Yeah, exactly.
Exactly. And then if you see a 1-star restaurant, like that's not a good restaurant, right? Let's go to the 3-star restaurant. So stars in that context suggest like increasing strength or increasing dose. True or false? Do we agree with that argument, right?
Yes.
Okay, good. So in this case here, p-values are being used here to indicate, in some instances, you see, based on this p-value, right? The p-value is being used to indicate increasing strength of association. But is that true? Is that what the value of p-values is? Can we ever use p-values to indicate the strength of association?
Yes, we can.
Okay, the answer is no, we can't. All right, so p-values are not meant to indicate the strength of association. What do we use in epidemiology to measure the strength of association?
Correlation.
Okay. Yes, but let's go. So this was a term we referred to earlier.
Confidence interval.
Okay, confidence. Okay, yeah, but specifically, what in general, what's the name we call them? We made reference to this earlier. It starts with the word E.
Effect size.
Exactly, effect size, right? What does that mean in simple terms? So let's look at this one here, for example. This is a great example. 2.73, 5.61. What is the effect size here? What do we see? All right, so Hill's criteria. Let's look at Hill's criteria for causation, right? Let's pick one of them, just a random thing. We'll talk about strength of association. One of the criteria here is saying what is the strength of the association between the cause and effects, right? That is what we're trying to capture with effect size. Lungile, are you here?
Yes, Prof.
Are you the one trying to it says a user is requesting remote control. Is that you?
No.
Okay, so
No.
decline. Okay, all righty. So a criterion for among the Hill's criteria is the strength of association. When people make use of the p-values this way, in their minds, they all, whether they know it or not, they are referring to strength of association, but that's not how we assess it in epidemiology. Strength of association epidemiology means that we look at the effect size. The ones that are bigger have a stronger effect. So here you can see that some has 2.73 and most has 5.61. So all things being equal, this is a stronger effect just based on the effect sizes. So we don't use the p-values. We use the effect sizes. The p-values are very easily manipulated by the sample size. If you have a very, very large sample size, you will always get very, very small p-values, right? So moral of the story, please, at least in the world of epidemiology, please, this is not good practice, right? It's statistical significance is either significant or not significant. There's no need to capture all of this. Plus, you've already given us the confidence intervals anyway, so why do you feel a need to provide stars? And then provide us ratings of the stars. So please, let's not do this. Let's not put this kind of gradation because it makes no epidemiologic sense. All right, now let's finally see if there's any other thing we can capture from here before we go on to write our own manuscripts. I'm curious to see how they report the inferences they make. Now, this is not wrong. This is not wrong, but when you're writing, you want to make sure that you make it easy for your audience. It becomes very tiring on the eyes for people to read, especially when you're putting descriptive statistics. Like everywhere, 26.9, confidence intervals. So you can make it easier for your audience by just reporting the estimates, because it now makes it extremely hard for reading. Now, it's a different thing when we're talking about measures of association like odds ratios, right? That one you can always provide confidence intervals. But when you're describing percentages or means, for the sake of reading and ease of reading, because at the end of the day, you are writing this manuscript for people to read and for them to understand. So make it easy for them. You don't have to put confidence. Of course, this is technically correct, but practically it's kind of hard for your readers to follow through. And then let's see. So here, about half of students, whoever tried, again, remember that when we weight analysis, the inferences is always on the general population and not necessarily, again, this is not wrong. They made reference to students. We don't know where they didn't say participants, but I cannot emphasize enough that once you weight your data, then you would have to make sure that the unit of analysis or the inferences have been made to the overall population. All right, I think we have had enough now. Let's now go over to our own study and see how we can replicate that. Okay, now, one of the things I would really encourage you to do is to take your own work or take a data set and replicate what they have done and get the same results. And I would rather encourage you to use an agency that you can trust. I can trust. CDC's work goes through very, very stringent checks. So it will be a very good place to start from. So go there, take an MMWR report. So let's look at one, for example, MMWR. This, for example. So the data sets are publicly available. Everything is publicly available. Take the analysis, repeat them meticulously, and you must make sure you get the exact same results. That tells you that you've done the work correctly. That gives you the confidence now to then take that work and then do with new data and spread your wings and fly. But the first step of learning will be to take this report and replicate every single report from there. And the MMWR also is a gold standard in how you should report science. They do everything by the book. And so in terms of, for example, the titles, every title should be descriptive and should contain elements of person, place, and time. So here, for example, estimated prevalence of tobacco use among high school and middle school students in the past 30 days by products, school level, sex and race, National Youth Tobacco Survey, United States, 2017. This is a gold standard on how to report titles. The titles should contain elements of person, place, and time. In this case, the person is among high school and middle school students. See, very well defined. Person, place, time. Epidemiology, this is a standard requirement in epidemiology. Science of, at least in descriptive epidemiology. So person is well described. Place, United States. Time, 2017, right? You can compare that against, for example, let's look at these authors, for example. Let's see to what extent they complied with that requirement. Factors associated with ever and current, this is good. Among Senegalese students, person, place, and time. That's excellent, right? So all of your titles should have that same recurring theme. Person, place, and time, right? Let's look at the other authors we looked at quickly then. Association between respondents' characteristics. No, this is not good. There is no person, place, and time here, right? This is saying we don't know who is the study population. We don't know where, what place, what time, what year. So this is please let's avoid this, right? Let's do like the other authors, and that's why you really want to follow. Good practice. You want to follow a report like MMWR to really understand the proper way of writing, and reporting things. So another thing that you also want to pay attention to is we don't want to report estimates that are imprecise, that are not reliable. Remember that we looked at suppression rules. The whole point of this guidelines is not just so we know them and just forget about them, is to implement them in our practice. NCHS says that how should we determine, the whole guidance here is saying, how do we report reports in a way that is reliable and trustworthy? So NCHS is saying that if an estimate is not reliable, don't report it. And this is how you're going to know that an estimate is not reliable. And so the implementation of this is done in MMWR very, very perfectly. So you can see here, estimates are not reported in many places. And if you look at the footnote here, it says data are statistically unreliable because sample sizes was less than 50 or the relative standard error was more than 0.3, which is obviously a percentage, or 30%. These are basic standards that we all need to know. Don't report estimates with very high relative standard error because they do not meet NCHS suppression guidelines. So if the relative standard error is more than 30%, do not report it. So that's a basic standard you all need to be aware of and implement in your practice. That's one. Then here, you see another very common estimate that is reported in reports like this is the total number of users in terms of counts. So here you have, for example, the estimates reported as percentage. So in other words, there are two ways we can report estimates. Please, can you mute yourself? Thank you very much. So we can report estimates as percentages, or we can report them and with also as counts. Why do you think it might be advantageous to report counts like 1.73 million? Why do you think this might be useful? Instead of saying 9. So here, for example, you're saying in the overall among high school students, 11.7% were users of e-cigarettes, or 1.73 million. Why do we need a 1.73 million? Why do you think that might be helpful? Can you think of any context or any context where it might be interesting to report that?
It shows the exact number, the exact estimate, rather than just the percentage. It gives a clear picture.
Okay.
Yes.
What audience might you be discussing with that might make that might resonate with them?
Policymakers.
Exactly. Policymakers. Imagine you tell a policymaker that, well, let's see. Oh, 0.7% of a youth population reported BDs. They're just going to say, oh, it's just 0.7%. Oh, it's not even up to 1%. But if you told them what? If you told them 100,000 youths in your constituency are using BDs, suddenly it doesn't feel like such a small number anymore, does it? Like, wow, 100,000 people. That's a lot of youth. And then this guy is now ready to go and get funding to stop this issue, right? And that's why we report these things, right? It's not necessarily for scientists per se, but an MMWR is a classic policy document where we want to move policy. We want to make sure that those people who need to take action have the data they need. Your job as a scientist or an analyst is to present information so that different people who need it can access it. Now, the question...
Attention! Attention! You niggers have been hacked by the CCP thugs! This Zoom meeting has been hacked by the CCP thugs! To the Chinese Communist Party, or you...
Please, can you remove that person, please? Jeez. All right. I'm sure that's the same person who wanted to take control over the meeting. All righty. Okay, so how do you think we're calculating this estimate? How do you think they're calculated? It says 11.7% of the youth, and so we have 1. How do you think, if you are the analyst and you ask, okay, don't just give us the percentage, also give us the weighted count. How are you, as an analyst, going to? Well, the goal here is to make sure that we train us as analysts, right? So if you are going to calculate that, how would you do it? Any thoughts? My question is, how do you think these numbers are generated? How do you calculate the 1.7 million people? It's obvious that we can easily calculate this as a percentage from the data, but how do you think these numbers are calculated? Okay. So someone say multiply the 11.7 with population. Yeah, that's in theory we can do that, but that's not how we do it. Because in that case, we will get wrong estimates. The count will be significantly different because here we're talking about our target population is kids who are in middle and high school, right? So first of all, we may not necessarily even have in the census the total population of those in school. The census may simply tell us the total number of youth in a particular age group. So we may not even have the corresponding number to be able to multiply. And also remember that in a survey like NYTS, it's not all middle or high schools that are part of the study population. They exclude certain types of middle schools and high schools. So the moral of the story is that it's almost impossible to get the number of the target population that were included in the study to multiply with against the 11.7%. And that's why we never ever do that. If you look at the methodology here, the methodology here says, let's look at this. Okay, national prevalence estimates with 95% confidence intervals and population estimates rounded down to the nearest 10,000 were computed, right? So they're not computed from a census, they're computed from within the data, right? So that's something that you also have to learn, right? You have to learn how to be able to generate that. So here are some of the things that we have to learn to do. We have to learn how to suppress estimates that are not reliable. We have to learn how to calculate weighted population counts. We have to learn how to accurately calculate the confidence intervals. And if you note here, MMWR obviously is not showing the n over n, the denominator and numerator, because clearly that makes no sense in this context. All right, so those are some of the things that we need to learn at the minimum to be able to serve as an analyst, so that when WHO or CDC is saying, hey, we need an analyst to analyze large population surveys, that way you are confident to apply, knowing that you can do the job, right? So those are some of the minimum skill sets that we need to develop to do that. So we're going to take the data sets and walk through this example. And I will strongly encourage all of us to be able to replicate that. The goal is, again, when you get back home or later in the evening or sometime in the week, you take the report and you do the exact same thing, and you should be able to get the exact same results, right? And so that's a very useful skill to have, to be able to analyze complex survey data. Yes, there are some hands up. Eric, your hand is up.
Okay, Prof, from the table that you just showed, like I can see some asterisks within it. So that one, what's the meaning of those asterisks within the table?
So they're just defining how it was calculated. So for example, this one here, any tobacco product use, they're saying any tobacco product was defined as use of any tobacco product, e-cigarette, cigarette, blah, 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 on at least one day in the past 30 days. Your tables must be able to stand alone, right? So they must stand alone. So that means that all the definitions, if you use an outcome or a variable that users might not know what it means, you must provide a footnote for each table. So you see every table or every figure, you have its own footnote, right? Because the idea here is that if you search this on PubMed, if you go to PubMed, for example, and you search for tobacco use among youth, let's say MMWR. So see here, you see how the figures are separated. If you click on this figure, the way it's separated now from the rest of the table, I should still be able to see key information about the figure, even though it is not part of the manuscript. So you should realize that in modern publishing, publishers will typically take a manuscript and separate out the different elements. So in that case, the user doesn't have the whole manuscript to be able to have context. And that's why it's your job to make sure that every single table and every single figure that you have can stand alone, right? Because then, even if the user is just reading that table or that figure in isolation, they still understand what everything means without having to go and say, oh, geez, let me go and look for the manuscript that this table came from before I can understand what a table is. That is why, again, in MMWR, this is the gold standard, because you see every single table has a whole set of footnotes. Figure has a whole set of footnotes. This figure has a whole set of footnotes so that it can always stand by itself, right? This is the gold standard. This is what you should be doing in your own work as well. All right, now let's replicate this MMWR and see how we can also generate exactly what it did, so that when you are replicating it on your own, you know what to do. So first, let's get the data. So NYTS data, CDC. So this is the website. We are looking for the data from the year 2017. So here you see, when you come, you see the NYTS data, format library. In SAS, you have different formats. In Microsoft Access, in Microsoft Excel, this was provided in the days when some software are very finicky, where if you want to read data, the data must be in a particular format. That's why we always used to provide data in so many different formats. But with modern platforms like on Chi-Square, it doesn't really matter the formats, the data set is in. You can always read from any format. And so the requirement here is not so much, it doesn't really matter which file you download. But with the traditional software, there are always requirements that it might have to be in this format or that format. And that's why you have this historical practice of giving you data sets in different formats. But so let's just download Excel. Now, remember we said you should always try and access as you're downloading the data set, you want to make sure you're downloading the codebook. And that's why they always put the data set and the codebook together for you, so that you as you're downloading one, you're downloading the other one as well. So let's download this. So typically it comes here, it's going to come here as a zipped file, because the items are in there together, zipped together. We zip to compress them so that it doesn't take up a lot of space. So you have to extract the file, right? So when you have a zip file, there's a button here. You click on extract. If you don't have a software to extract one, just Google free software to extract files, and you can extract it accordingly. So I'm going to click on extract all. It's pulled up. Here, I can now select where I want the file to be saved. So I can just browse and specify a folder where I want it to be saved, right? I can say, let me save it on my desktop. And let's call this, let me create a new folder. You can create a new folder and call this last day. And then select that folder and then extract into that folder. So now my folder here is in last day now. So if I open it now, I can look at the data set, I can see the codebook. Always open the codebook. Don't just download the data set and read it and just think you are home and dry. The codebook is what allows you to be able to recode things correctly and do things the right way. So we've opened this. Now we're going to go and import the data into our software and start our analysis to make sure we get exact same results that were published in the report, so that we can see how we can do every single thing by yourself. So I'm going to click here, go to Chi-Squares. Again, for those of us who don't know, we can access the Chi-Squares platform. This is the website. And if you have an account, you log in. If you don't, you sign up. So I'm going to just log in. All right, so I'm going to come with data analysis and start a new project. I'm going to call this NYTS analysis day 5. Is it day 4? Day 4, okay. And the purpose is to replicate results from the NYTS CDC reports. Now we would upload our data sets. You can upload different formats, whether it's CSV, Excel, JSON, Parquet, or whatever format it is. So let's upload. We're going to go to my device and pick from where we had it. So desktop, I think we called it last day. This is the file. I'm going to upload. Okay, so it's finished. We can now proceed. So it scans for missing values and does a lot of quality checks in the background. It makes sure that everything you're doing, it makes sense. So if you have variable names that are bad, it's going to flag them. But well, everything is fine now. So we can, again, remember the lessons from the past few days said, when you upload your data set, make sure you do some basic checks. Check the number of columns. Is it what we expect? the number of rows, is it what we expect, right? Make sure you at least cross-reference that with what you expect. So here, summary of data sets, number of observations, 18,872. That's what we expect, right? Number of columns, and so you want to make that basic checks, right? To make sure that it's what you see is what you expect to see. Now, the analysis mode here is unweighted. We're going to change this later on to weighted. In fact, let's even change that now. Why weighted? Because let's go back to the MMWR report. Look at analysis, the statements here. Data were weighted to account for the complex survey design and adjusted for non-response. That is an extremely, extremely important statement, right? The data come from a complex survey. And by complex survey, we mean a survey where we use cluster sampling. And because of the cluster sampling, there are different probabilities of selection. In this particular survey, we use a 3-stage cluster sampling where in the first stage, we selected counties, and then we went to, inside the counties, we selected schools. And then within schools, we selected classrooms, right? So the probability of selection equals the probability in the first stage and the second stage and the third stage. Some people will have a bigger probability, others will have a smaller probability, right? And that's why the N over N was not adding up to the estimate then. So when you're analyzing, you must account for it. If you don't account for it, you're going to get results that are completely invalid, like completely. So traditionally, analysis of weighted data has always been a nightmare. That's why most people don't do it. Again, most people struggle. It's a nightmare for most people because it's a lot different from analyzing the traditional way. For every test you're doing or every procedure is a completely different setup with complex survey data. So it's almost like you have to learn two different analyses. You have to learn how to do a chi-square test the normal way. I have to learn to do a chi-square test with weighted data, right? It's like, wow, you're living in two different universes. So that's one of the things we've done on the chi-square platform. We've simplified the whole process. The researcher doesn't have to worry about, oh, geez, what's the test for weighted or what's the test for unweighted? No, you just upload your data set and set the data to complex survey mode. And that from that point, the platform will automatically handle everything from that point. So let's set our data to complex survey mode by selecting our weight variable, PSU, and stratum. The weight variable, so think of it as the weight variable controls the estimates, right? The PSU and the stratum control the variance. Remember on day one, we established that everything we do in statistics, we're always asking, what is the answer and how sure are we? What is the answer and how sure are we? Everything in statistics, that's what we do. The weight estimates make sure that the answer is correct. The PSU and the stratum variables make sure that the confidence intervals are correct. So you need both. You need to make sure that the point estimate is correct and that the confidence intervals are also correct. So here, we're going to select the weight variable. The PSU is going to select the PSU variable, PSU, and the stratum, select the stratum. Now, if you notice, there are many stratum when we searched, and the reason is because you have V stratum 2, V stratum, some particular software like Sudan or SAS callable Sudan require the variables in a very specific form. So generally, CDC will have to create, attend to the very specific needs. On the chi-square platform, it doesn't really matter, right? All of those things are automatically accounted for. So the platform doesn't require a variable or a data set in a particular format. But just to explain to you some of those nuances. So now that we have selected our 3 variables, we can now save. And now the analysis mode has changed from unweighted mode, it's now to weighted mode. Now, the next thing for us to do is to generate the outcome variables. Those are the prevalence estimates for the various tobacco use. Cigarettes, e-cigarettes, cigarettes, cigars, we need to record them in a way we can analyze. In general, for prevalence estimates, the variables must be in a binary form, 0 and 1, before we can analyze them. So we need to recode all of them so that 0 means non-user and 1 means a user. Now, let's go to the code book and let us make sense of that there. So when we go to the code book, we can see the table of contents down here. So when you're browsing through the code book, just before you start reading meticulously, always just sample through it and see how things are laid out. In almost every code book, there are two sets of variables that you will find. The first set of variables are the variables that were captured in the questionnaire originally. Like you see QN86, QN whatever, that's the original set of variables. And then you will see a set of variables that are recoded by the agency to make things standardized so that reports, data from this report can be comparable to another report. So you can see here, record. Those have already been recorded so that we can allow things to be standardized. So I'm trying to read the question. Why must we determine the weighted variable? Okay. I think there's some confusion as to what weighted analysis mean. When we analyze data from a random sample, this goes back to the Excel spreadsheet I mentioned here. Remember we said in the first scenario, we had a case where everybody had a weight of 1. When we draw a random sample, if I draw a random sample of people in the country, a simple random sample, everybody has a weight of 1. Everybody has the same probability of being selected. That is the hallmark of a simple random sample, equal selection probabilities. Now, in many other cases in the real world, we don't have equal probabilities of selection. In almost any national survey you have, the probability of selection is not equal for everybody that took part in that survey. So you have a scenario where different people have different probabilities of selection. My probability of selection might be 0.5, yours might be 0.2, his might be 0.1, right? And so on. The weight is simply equal to 1 divided by the probability of selection. That's how we calculate the weight. Weight is equal to 1 over the probability of selection. So if the probabilities of selection were not the same, that means that the weight will not be the same. If I took a random sample and everybody has the same probability of selection, everybody has, let's say, 0.2, 0. Then that means that the inverse, 1 divided by the probability, will be the same for everybody. And if the weight is the same for everybody, then it's a self-weighting sample, right? So that is why we need to do weight. We need to use weight because when we're sampling, we might have oversampled some people because, you are not the one coming up with the probabilities. They in the data set you downloaded, those weights are already there. The weight variable is there, the PSU variable is there, the stratum variable is there. Like we did not come up with those variables ourselves. They were in the data set when we downloaded them. So your job is not to create the weights or to create the PSU. If you want to learn those things, we have a more advanced class for people who are doing the back end, right? Your job as an analyst is not to create the weight variable or create the PSU or create a stratum. Your job as an analyst is to know how to use them in the analysis. So for the sake of this session, don't worry about how they were created, right? You should have a very big picture idea of the problem that the weights are trying to solve and why we need them. And why do we need them? Well, we need them because the probabilities of selection in our sample were not equal for everybody. And so to solve that problem, we need to use weights. So that's a big picture. And those weights were created by the agency that collected the data, right? So that's the big picture. Now, we have to create the variables that we need for our analysis here. So if you look at in the code book, we have these variables, C cigarette, and we have C cigar, and all of that. So we need to, from these variables, create the variables we're going to need, right? This is the percentage of all students who reported the use BDs. C cigarette means the percentage of all students who reported smoking cigarettes on at least one day in the past 30 days. So let's see what the values are for this. So you see here, individuals who answered yes have a code of 1. Individuals who answered no have a code of 2. If you do not weight the sample, here's what will happen. Let me show you what might happen. Let me look for a document to show you what happens when you don't weight the data. I hope I can find this. Just give me a second. Let me look for something quickly. But the moral of the story is that if the data were weighted or need to be weighted, but you don't apply weights, your results will be invalid, right? And I'm going to show you, I'll go back to the Excel spreadsheets and show you quickly so that we can compare. But for now, I wanted to show you in practice what will happen. Okay, I was looking for a PowerPoint that had a very nice slide on that. But let me show you in principle. Forget about that. Let's look at it empirically from the data. So we have our sample. Let's open a new spreadsheet. So we have, this is our data set. It's a small data set. This is individual number 1, individual number 2, number 3, number 4, right? This is a non-tobacco user, tobacco user, tobacco user, non-user. Now, there's a weight variable in the data set that came with the data set, right? We're going to assume 2 scenarios. One scenario is that we use the weights. The other scenario is that we did not use the weights. And let's see what happens when there are weights, but you completely ignore them. All right. The prevalence, that the way your computer is computing the prevalence is that it's saying that, so if there's no weight, that's the same thing as everybody having a weight of 1. So no weight means everybody has a weight of 1, right? That's the implication of it. So when you have a weight variable, but you ignore it, here is how your software is calculating the prevalence. It is calculating it as the way we described earlier. It is taking the value of this individual times their weight plus, but we now move to the second guy, the value of this guy times their weight plus the value of this guy times their weight plus the value of this guy times their weight, right? All divided by the sum of the weights. So this is what your software is doing when you say, give me the prevalence divided by sum of all the weights. Oops. So the prevalence here, when the data on weighted is 0.5, right? That's what you get. Remember that a weight here means the number of people that this guy stands for. So a weight of 5 means that this individual on row number 1 stands for 5 people, including himself. This one stands for 1 person, just stands for himself. The weight of 6 means that this guy represents 6 people, including himself. When analysis are unweighted, you are saying that, oh, guy number 1 just represents himself. Everybody represents themselves only. That's what you are saying when the analysis are unweighted. So here, we get a value of 0.5 when the estimates are unweighted. So unweighted equals 0.5. But when it's weighted, let's put this here. Okay, let me just weighted. Let's just this is equal to this times this plus this times this plus this times this plus this times this, again, all divided by sum of the weights. Oops. Okay, this is a terrible example because, you know, the weights are, so let's inflate the weights. Let's say that the weights are very different, right? So you see, the more different the weights are, you are going to have quite dramatic differences in the estimates, right? Bottom line is that you are going to get results that are different from a scenario that assumes that, well, this guy represents 100 people, but you are saying it represents one person, right? That's why you must, if the data has weights, you must weight the data. Otherwise, the result will be invalid. You end up with a result of 0.5 when it's 0.77. Or if the weights are extreme, the results are going to be quite different, right? So that's why you must weight the data when they are. And and for your own, even for your reputation as a scientist, manuscripts have been retracted because you used the wrong, because what you've published is completely wrong. So for your own reputation as a scientist too, you need to know how to do correctly. Imagine you use a data set that has weighted analysis and you do not account for the weight. Yeah, that paper is going to be retracted, unless, it's or at the very least erratum, right? Yeah, an erratum will be issued because what you have communicated is completely wrong. And so, because the data require weighting and you do not use weighting. So, it's not a trivial issue at all. You have to be able to analyze data. And if you're trying to work with agencies like WHO or CDC, well, this is almost a very required skill. The first question they're going to ask you, can you analyze weighted data? The answer better be yes. So for many reasons, you need to be able to develop expertise in the analysis of weighted data. All right, let's go ahead with analysis now. So we're going to recode this variable so that we have one is yes and 2 is no. We're going to recode this such that 2 becomes 0 and 1 remains yes, because we want to recode them as so that the variables are binary, 0 and 1. So let's recode the variables now. And again, we have weighted the data by simply supplying the variables. On the chi-square platform, you don't have to do anything further. Your job is simply to come to the analysis mode and supply the weight variable, supply the PSG variable, and supply the stratum variable. And your job is done. From there, henceforth, the platform takes over, right? On other platforms, obviously, it's a lot more manual wrangling with the data. But on the chi-square platform, that is the only thing you have to do to weight the data. So from now henceforth, you have done your job, and the analysis are all going to be weighted from this point onwards. I hope that is clear. If you want to now change it back to unweighted, you simply come to this point and uncheck this box, and then and then you save, and the analysis will become unweighted. All right, but now we obviously want our analysis to be weighted, so we're going to save this here. All right, let's go ahead and create our variables. So now we want to recode our variables. Let's do that. And so come to data processing, we come to recode. Data processing, we come to recode. And we want to recode current cigarettes. But we also want to recode other variables. So this is where you can use the batch mode, batch record. Batch simply means whatever you're doing to that variable, do to all these other ones as well. That's what it means. So let's enable batch recode, and let's select the variables that we want to have in our batch. Let's select BDs. Let's dissolvables, snus. The C stands for current. So these are all the variables that are in our report. So select them. All right, so I think we've selected all the variables that we need, and we click on done selecting. So what we're doing now is simply to recode the variable, because for us to calculate prevalence, we need the variables to be 0 and 1. The variables were not 0 and 1. The variables were 1 and 2, as you can see here. So what we're just doing here was we're saying, well, let's change it from 1 and 2 to 0 and 1. The 2 means not a user. So we just want to come to more actions, edit label, and change the 2 to 0. And that's it. So that's all we're doing for recode. So the platform will then apply the action that we apply to this one to all these other ones as well. That's in the batch mode. And the platform also automatically creates names for the variables. So CBDs has changed to CBDs_R, where R stands for recode. So the platform automatically suggests the names. You can choose to keep them the way it has been suggested, or you can change them if you want. For the sake of this demonstration, we can just change and keep them the way they are. All right, so our outcome variables have been created. Next, let's record the variables that we need for the demographic variables. We have variables in that MMWR like sex, and race, ethnicity. So let's record them. So let's first of all select sex. Sex. Nope, sorry. Let's look for sex. And let's click here to recode sex. It's 1 and 2. We need to know what 1 is and what 2 is. The only way we can know that is to go to the data dictionary. We can't just guess that 1 means male or 2 means female. So we have to go to the data dictionary and search for sex. So what is your sex? 1 means male, 2 means female. So let's record them accordingly. So 1 means male, edit label, male. It's only the outcome that we need it to be 0 and 1. The other variables can be descriptive so that when we're interpreting the results, we know what they mean. So 1 means male, and the platform picks up colors for common things. So male is blue, females will be pink, for example, so that it's intuitive. So this is the visual way of recording. 2 means female. All right, so let's give the name as gender. So we're done with that variable. The next variable we need to record is race. So let's record race. Let's look at the MMWR, the code book again, to know what the race means. So find race M. 1 is white, 2 is black, 3 is Hispanic. If you look at the report, they have white, black, Hispanic, and then other. All others are grouped under other. So look, the footnote says blacks, whites, and others are Hispanic, and others could be of any race. So we're going to collapse all the others into other. So go back to our, so 1, we'll edit the label to call it white. Confirm. 2, we edit the label to call it black based on what we just saw from the report. 3, we edit the label to call it Hispanic. Then 4, 5, 6, and 7 were collapsed into one category as other. So we're going to say 4, 5, 6, and 7. We're going to merge all of it selected. And so it has merged them into one. And we're going to call that edit the label and call it other. So now we've recoded race into 4 categories. So I'm going to call this race 4. The only way you can master this is to go and do it yourself, right? You have to practice this over and over. So this is just to give you some high-level guidance so that when you go, you can watch the video and then repeat it yourself. That's the only way you develop expertise. So proceed. So we have race created. The next variable we have to create is school level, which is middle and high school students. So we have to look for school type. Whenever you are recording variables, you should always try to make sure that you don't replace the original variable. So for example, let's go back to the race variable we created now. You see the original variable is still there, so that you can always go back to it and record it again if you want. So now, if I wanted to just collapse 6 and 7 into one group and maybe 4 and 5 into another group, I can do so, right? So this button here, don't ever use this checkbox. This is a very, very bad checkbox or dangerous, but we have to provide it because that's standard statistical practice that, well, in some use cases, you might want to replace the original variable, but this is not something you want to do in general. So as a rule, never ever, it should be very rare that you replace an original variable because that could be dangerous. Okay, now let's look for school type. And let's record it. So again, based on what I saw in the code book, this is high school students. And the other one is middle school. Again, don't just assume you have to read. You have to read the code book, right? So middle school and high school. And let's call this grade. All right, let's see what other thing we need from that report. Go back to the reports. So we have created sex, we have created race, ethnicity, we've created e-cigarettes, cigarettes, cigars, smokeless tobacco, hookah, pipe, any tobacco use. Let's create a variable called any tobacco use. Any tobacco use says here that you use at least one of the tobacco products in the past 30 days. So let's create that. So we can come back to here and let's create. So there are 2 variables we need to create there: any tobacco and any combustible. So if you looked here, it says any tobacco products and any combustible products. Any combustible product says you are said to be any combustible user if you use cigarettes, cigars, hookah, pipe, or biddies. So let's create that one first. So we'll come to data processing. We'll come to create composite variable. Composite variable, a composite means something that's made up of 2 or more things. So create composite variable using conditions. In other words, we want to use rules to create a composite variable. So click on that. And the variables we want to use are if you use cigarettes, if you use cigars, if you use hookah, if you use pipe, and if you use biddies. Those 5 products, based on what we saw there in the report. See, the report had 5 products. So now we have this, the variable selected. You can click here to maximize the screen so you can see everything on one screen. So you are set to be a user of any combustible product if you answered 1 here, or 1 here, or 1 here, or 1 here, or 1 here. If you answer all of this, we're going to merge the selected. So this is 1 or 1 or 1 or 1. We're going to drag this to this side. This is the side for when we have completed the action. And now for all the other ones remaining, we're going to merge them into another category of non-users, exclude missing values. So now we have, these are the users, 1 or 1 or 1 or 1, people who answered 1 to any of those 5 products. So let's just edit this label and call it our 1. And we'll edit this other one and call it our 0. And let's confirm. Let's go and give it a new name as current combustible. And let's create a variable. The system automatically tries to see if we have done something wrong. Now, the system has flagged that we have a problem with our variable. Somehow, the way we created it, some categories overlap, but the platform automatically takes care of that. All right. So there are lots of validations in the background when you do the visual method to ensure that you're not making a mistake, and the platform automatically takes care of all of those things so that you're not writing logic that doesn't make sense. All right, now let's go ahead and set up our variables. Our goal here is to calculate the prevalence of any tobacco use. Let's go back to our report here. We want to create among high school students prevalence of e-cigarettes, cigarettes, cigars, right? And calculate it overall and by sex and race. We also want to make sure that we suppress estimates that are not reliable, and that we also calculate the population count. We want to do all of those things at once. Let's see how we can set that up. We can come here. Where's our analysis? We come to estimates. We come to prevalence estimates. We'll come to select our outcomes. Let's select a few of the outcomes so that we're not overwhelmed. So we can just focus on just a few. Let's select cigarettes, cigars, smokeless tobacco, or let's look at just the major products, and electronic cigarettes and hookahs, right? Let's focus on 4 products so that it's easy for us to just focus on what we're doing as opposed to being overwhelmed. So we have selected 4 products. Our goal is to calculate the prevalence for those 4 products: e-cigarettes, cigarettes, cigars. Right, let's so e-cigarettes, current e-cigarettes, current cigarettes, current cigars. Let's remove cigars so that we just look at the first 3 products. So we're trying to look at prevalence of cigarettes, cigars, and electronic cigarettes. And let's click on done selecting. Next, we have to select stratification variables. The stratification variables are simply saying, what are the variables we want to break down the results by? In other words, we want to break the results by sex and by race ethnicity. So those are our stratification variables: sex and race ethnicity. So let's select those as our stratification variables. We are interested in race ethnicity and in gender. So those are our 2 stratification variables, and we'll click on done selecting. Next, this one says choose time variable for trend analysis. This is not applicable because we're not looking at trends over time. If we're interested in like a time series analysis, then we'll select a time variable. In this case, that is not our interest, so we'll leave that blank. Then this is a very important checkbox. Also compute weighted population count. In other words, it's saying, do you also want to calculate this estimate here? Where is the estimate? Do you also want to calculate population count? That's what the system is asking you. Yes or no? Yeah, in this case, yes, we want to calculate population count. So we'll check that box. Yes, calculate what population count for us as well. And we can use the rounding here. We can choose the rounding. And why do we care about rounding? If you look at the estimates from the report, you see how everything is rounded up very nicely? See this very nice rounding of all the estimates. And if you go back to the report, you will see that it says national prevalence estimates to 95 confidence intervals and population estimates rounded down to the nearest 10,000, right? So we need to be able to round. So that's what the system is asking you. Do you want to round the estimates or not? So let's round. Let's choose desired rounding. And we can round to the nearest 10, the nearest 100. Let's do what the report, exactly what they did. They rounded to the nearest 10,000. So let's select that option and apply. So what have we done so far? All we've done is select our outcomes, cigarettes, cigars, electronic cigarettes, which are the outcomes we have here. For the sake of this, we just selected the first three: e-cigarettes, cigarettes, cigars. That's the outcomes. Next, we've selected the stratification groups variables, which are sex and race ethnicity. Next, we've selected that we want the system to also automatically calculate this count for us. And we've rounded up the counts to be consistent with what they did in the reports. So those are the things we've done so far. Next, we want to make sure we suppress estimates that are not reliable, right? Estimates that are not reliable should not be included. So we want to exclude groups that are not reliable. So let's actually add pipe tobacco so that we can see how the system suppresses it. So we'll go back to our report, our setup. Let's add pipes quickly. That's a product that is really small. Pipe, current pipe, good. So we have the outcomes. We have stratification variables, which are race and gender. We have said the system should compute weighted counts. We are doing analysis not in the entire data set. Remember that the analysis, they did it separately among high school students. So all the results are seen here among high school students, and then separately for middle school students, right? You should be able to execute subset analysis. That's what we call subset analysis. So you have two separate subsets: high school and middle school. If you do not specify a subset, you are saying that you want to calculate it for high school and middle school students combined. That's what the entire data set means, because you have high school and middle. But that's not what they did in the report. The report did subsets. So let's also do subset as well. Let's create subsets, and let us say that our subset is defined by your grade level. If the value of grade level is exactly equal to high school, that's the people we want to include in the first subset analysis. You can also check the sample size for that group. So here we know that there are 10,186 students who are in high school who meet this criteria. So let's walk over what we've done again. We've selected the outcomes. We've selected the stratification variables. We've told the system to calculate weighted population counts for us. We've told the system that we're not analyzing the data among everybody, but among a subset. And the subset is kids who are in high school, based on what we are just trying to replicate what's in the report here, right? Based on what we see here, high school students. Among high school students, what's the prevalence of e-cigarettes, cigarettes, cigars, and pipe overall, and among by sex and race ethnicity. That's what we've done so far. Now, let's account for these checks, these suppression rules. The MMWR said that the suppressed estimates whose relative standard error was more than 30%. That is a gold standard. If you're going to be an analyst, especially if you're going to be working with large data, you need to understand relative standard errors and how we use them in practice. So that is a very important suppression rule used in globally in a world of complex survey data. So, and the common threshold is estimates with relative standard error of more than 30%, right? So let's suppress that. So we'll come here. Let's go to preferences. The preferences give you a lot of options to control how the analysis should be performed. So we'll come to preferences. You select the number of decimal places you want. We want one decimal place. You specify whether you want estimates with confidence intervals or with standard error. In this case, the report used confidence intervals, so we also were going to use confidence intervals. Next, the estimate says, do you want to suppress unreliable estimates? Yes, we want to. So you check that box. And next, it says, what threshold of relative standard error do you want to use to suppress? Well, the report used a cutoff of 30%. So we're going to use 30% as our cutoff to suppress estimate as well. And we apply. And now we're ready to run our analysis. So let's click on estimate. So the platform takes all of those parameters that we have specified, and now it has calculated all of what we needed. So here you have the prevalence of cigarettes, cigars, electronic cigarettes, and pipes. Overall, and by race, by gender, based on what we had in the report. You can see that estimates that are not reliable have been suppressed automatically. You see, current use of pipe was not reliable among Blacks and among people of other race, right? Let's see in the original report too. Pipe tobacco use was suppressed. Let me make this smaller. So use of pipes was suppressed among two groups here. You see the same groups here, Blacks and among other, right? Exact same thing here. Based on the suppression rules we've specified, people who have race Black, see, suppressed. Individuals who have race other, suppressed, based on the suppression rules from the NCHS as we specified in our report, right? And the platform also computes the estimates, the weighted population counts. So you see, current use of electronic cigarettes, 173 or 1.73 million people. Is there a way I can make this side by side? Let me pull this out and let's compare them side by side. So this is what you need to do. You need to calculate estimates and you need to be able to match what you are calculating. This will increase your confidence in your ability to execute what you're doing, right? So current cigarettes smoking, total number of individuals among high school students, 1.12 million. Current cigar, let's look for cigars, 1.14, now 1.13. Now you might get differences based on the rounding differences, but that could be expected in some instances. Current electronic cigarette use, we have 1.73, and so on and so forth, right? Pipe tobacco use, 120,000, right? So you should be able to match those results accordingly. The most important ones here will be our estimates for overall use, right? You should be able to, again, compare what you are getting with what is reported in the report. So for example, in the overall population, which is this one, the total here, prevalence of e-cigarettes use is 11.7%. So that's what we have here, 11.7%. Prevalence of cigarette smoking, 7.6%. Prevalence of cigar smoking, 7.7%, 7.7%. And prevalence of pipe smoking, 0.8%, pipe smoking, 0.8%. You should be able to match those estimates exactly like that, right? That tells you that you are on the right track with your learning. And so that's how those requirements map onto the execution on the platform. Now, if you want to now write a report, all you need to do is push your results to a manuscript. So we're going to create a new manuscript and call it tobacco use among US. Geez. My keyboard is sticky. Among US high school students. Let's generate the aim with AI. So your estimates, the prevalence estimates should match exactly. So that would be your homework. That also adds to your confidence that, okay, now I can analyze complex survey data accurately. So let's push our results here. All right, let's view the document. So this is the report we have. Let's make these variables to be human readable. So we have the start of our report. This is the results that we've captured. So as shown in table 1 and figure 1, prevalence in the study population, in this case, the grade was high school students, and the total was N101, 10,186, was as follows by outcome. Current electronic cigarettes, 11.7%, current cigar, 7.7%, current cigarette, 7.6%, and current pipe, 0.8%. The table 1 and figure 1 reports stratified prevalence estimates with statistically significant within group differences seen at the 5% alpha threshold. Subgroup differences in the outcome variables, cigarettes, cigars, electronic cigarettes, and pipes were evidenced by significantly varying estimates at extremes of prevalence for the following groups: gender and race, right? And then the results are reported. Notice that wherever p-values are reported, you have the actual estimates shown. 9% among group female versus 6.3% among group male. You have a chi-square statistic at 1 degree of freedom and a p-value. This is a gold standard for how you should report prevalence estimates, right? So the platform automatically writes out the results for you so that you don't have to, in case you don't know how to write it properly, you can at least get some support in that regard. So this is how you write them. This is how the results are presented in your tables and figures appropriately as well. This is the table we just generated with the estimates by the various outcomes and the suppressed groups as well. Your tables and your figures must be able to stand alone, right? The platform provides some footnotes in that regard. Here it tells you that the denominator for the analysis was those meeting the following inclusion criteria. Grade equals high school, and this was the sample size. It says that data were weighted. It says unreliable estimates where the relative standard error was 30% or higher are not displayed and are flagged with an asterisk where present, right? And so that provides context. So an individual looking at this is not wondering, what does the asterisk mean? So this is a good practice for you on how to report estimates. And here you have the weighted counts provided for the groups. So that is how you analyze complex survey data. I think we're on time now, so we're going to stop there. But again, you have to practice. So your job is to really, and the Catch platform really makes this like exceedingly. I cannot even tell you how easy it makes your life for you. Because again, all of these things you'll have had to do them, quite separately. Calculating the relative standard errors, calculating the population counts. But again, the whole point is not to make things harder for people, but to make things easier for people. All right, I'll take questions that are remaining now.
Thank you, Prof. Any questions? We will now share the attendance register. Please look out for it and complete it. We have a question. Okay. Prof, do you have anything to say about the homework since we didn't get a chance to go over it?
We can organize another session to go over the homework. maybe next week. So Lungle will go over the homework. Lungle is the teaching assistant for this course. So we'll go over this. We'll go over the homework. I've just the teaching assistant.
See, now people won't join.
So that's what we're going to do. Okay.
Okay. All right. So questions. After weighting the data, is it advisable to do multi-level analysis for survey data? If so, why?
What do you mean by multi-level analysis? The person can unmute and ask. Well, that means different things to different people. Can the person provide context for what they mean by multi-level analysis?
All right, Theophile, we're waiting for you. In the meantime, I'll continue reading. Okay, I've listened and learned. I still need more learning to do better, but my question is, what is the edge of chi-squares over other platforms and apps?
Well, the edge of any platform is relative to your own context. So you get to answer that question yourself by saying, what are my unique needs and how does any platform? The question is never about tools. The question is how do my needs get met? So whichever platform or tool meets your need, that's what you should go for. So that question is, I can't answer that question for you because it's that's a question you'll have to answer based on your own use cases.
How can you recover if you mistakenly replace a variable?
If you replace a variable, the platforms, when you, the options will be to go to your history. Let's go back to switch to analysis. So under analysis history, if you, let's say, deleted a variable, you can, we've not deleted here, but you have options to recover. So that allows you to recover. If you've replaced the variable, well, you can restore that data set to an earlier point in time, or you can re-import the data set. But again, prevention is better than cure, right? That's why we're emphasizing over and over. Because if you revert the variable data set to an earlier point in time, you might then miss changes that you did to that data set. So just develop a culture of not replacing variables. And then you don't have to worry about that.
Thank you. Can the platform also calculate weighting when they are using primary data? What additional variable?
So if you are doing data, if you're trying, let's say you collected data and you now have to generate the weight yourself, you come to data processing, you come to create calibration weights. That's an entire whole system entirely that allows you to generate calibration weights. And when you are doing your sampling, the platform also allows you to create, base weights or design weights. The final weight is always equal to the base weight times the calibration weights. Calibration weights are trying to correct for non-response bias. It's not something we can answer in 5 minutes. That's an entire PhD on its own. You can do a PhD in just weighting. But we're having sessions on advanced survey design for people who are survey methodologists and who want to really understand the nuances of how these things work. So you can definitely join the sessions for those ones. All right, any other questions?
Can the chi-squares platform be used for dynamic regression model, and will it be helpful for data preparation before the dynamic regression itself, like created slopes, steps?
Well, you can explore the platform on we have about over a dozen regression methods that the platform supports. We're always rolling out new methodologies after very careful assessment of quality. So you can always check. There are, of course, a lot of data preparation steps provided here to assist you in preparing your data. But there's hardly any data preparation step you'd want to do that you won't be able to execute on the platform. So the bottom line is platform allows you to do anything you would do elsewhere, but in a way that is much more visual. And much more simpler. So that's the because we at Chi-Squares were huge believers in simplicity. That life is not that hard, and so that's the value indeed there. All right, any other questions?
Thanks, Prof, for a wonderful work done. Can you suggest some textbooks as a support to us as we practice?
Geez, textbooks. That's a hard question. Textbooks on, well,
you can tell us you're writing one.
have not really met a very great textbook for complex survey methodology that but anyway, we have a hand for all it's worth. We have a handbook, that a manual, a guide. So maybe we can share the guide that the step-by-step guide, so that people can just follow step by step in analyzing data.
We'll share it when we share the summary. Okay. Michael, please take note. How can we get the code book for data analysis?
Wherever you download the data set, the code book should be there. So wherever the data you accessed. So you see, in this one we did, the code book and analysis, the code book and analytical data set were together. So they will always be together.
Can the platform be used to analyze qualitative data?
It's not a platform for qualitative data. You can collect, the platform is, provides end-to-end support for research. So you can design your surveys and collect qualitative data, but the analysis engine is not designed for qualitative data. It's designed primarily for quantitative data.
If there are any other questions, please post them right now. If I missed anything that you might have posted earlier. Okay, here's one. Is it advisable to report the p-values for binary logistic regression in your manuscript? I ask because sometimes you want to show the variables with p-value cutoffs of 0.20 that you include in your multivariable analysis.
Yeah, you can report p-values. You can report p-values. You can report confidence intervals. That's the choice. But yeah, you can do so, absolutely.
Is this training continuing? Oh,
but
sorry.
So to clarify, I see a p-value 0.2 threshold. I want to clarify that. So I use this. I said the 0.2 cutoff I referred to yesterday was when we are trying to assess for confounding. When we're trying to determine confounding, we usually use a much bigger p-value. I did not mean that in your routine analysis, in your main analysis, that you'd use a 0.2 p-value threshold, right? I mean that in assessing for confounding, that we use a threshold. So if you do a regression analysis, for example, right? Let's say I'm trying to do a regression analysis, let's say regression, and I select a binary logistic regression. I'm trying to look for factors associated with current combustible. I select, for example, grade and race and gender, right? The platform assesses them not at the, so let's quickly run this estimate to see what we're talking about. That will answer the question about presentation of cutoff and presentation of p-values. Let's give it a second. All right, so first of all, as you can see, the platform will present your regression analysis for the analysis performed and report both odds ratios and 95% confidence intervals, as well as p-values, right? So you can see, report the p-values accordingly. When reporting p-values, you must use exact p-values. What does that mean? 0.766, that's an exact p-value, except when the p-value is extremely small. So you see here, the platform uses less than 0.01 because the p-value is extremely, extremely small. And so that's the only way it can be reported. But in other words, in other context, you have to use the exact p-value. Now, when you are reporting, look at the text here. When the platform writes out the results, in this case here, you see it says the following factors were inversely associated with current combustible at the set p-value of 0.05. This is the p-value threshold the platform uses for analysis in general. Grade coded as middle school versus high school. Adjusted odds ratio is 0.19 with 95% confidence intervals from 0.15 to 0.25. And race coded as other versus white. Odds ratios 0.63, confidence interval from 0.46 to 0.85. The remaining results were not significant, right? So in this case, the platform uses the p-value, the traditional p-value of 0.05 as the cutoff for significance. So that if you were to push these results to our analysis and go and see that, again, all the results presented and all the evidence evaluated in the manuscript writing is at a level of 0.05, so that, we're all on the same page. So emphasizing again very clearly that 0.2 we mentioned yesterday was only for when you are trying to assess for confounding, right? Not for the entire manuscript. There will still encourage you to use the traditional p-value of 0.05. So now we have our odds ratios. Again, our odds ratios here are all, if you can see the null value, everything is evaluated at the level of 0.05, right? And the results you see presented in the manuscript accordingly reflect that threshold as well. So let's not get confused between that 0.2 threshold we mentioned and the 0.05 traditional threshold for significance. All right, next question, please.
Thanks, Prof. Okay. Sorry, I'm checking.
Okay.
Can we upload a collected data saved in Excel format in the platform for statistical analysis?
Yeah, you can import data in whatever format. And, whether it's Excel, CSV, Parquet, whatever format it is, the platform accepts all.
Can the platform check questionnaire validity?
Yes, you can. If you are creating your questionnaire, you go to the survey data collection part of the platform. And if you, let's say you have a random survey, if I wanted to import from a Word document, you can upload a document, and then part of the options is that it should check for validity, and it will do so accordingly. So you have the option to say, let me see if I can just upload something here. Well, you can try it. That's your homework. Try create the questionnaire, and the platform, you can definitely specify that option for the platform to check for validity, in which case it checks whether the language of the questionnaire is double-barreled and whether there are leading questions, and it will try to reframe them in ways that are more accurate. But yeah, that's under the survey design. All right, any other question?
Is determining weight optional to a primary data set analysis?
Is determining weight?
Yeah, determining.
Well, so you're saying that you did your survey, and you're like, should I use weight? Should I create weight? Well, that depends. You are the investigator. The question is, we have to understand the cycle of inference, right? We take a sample from a population, and from that sample, we make inferences back to the population. That cycle depends on random selection. So sometimes I may have a sample that is no longer representative, and I want to make inferences to the overall population. Well, you have to then compare the sample and the population. For example, in my sample, if 20% of the sample is male, but when I look at the overall population, 40% are male, and I see that maybe 20% are aged 20 years or older, that in the overall population, it's maybe 50%. Clearly, it's clear that my sample is not like the overall population. Something is wrong. So the question is, how then do I make the sample to become like the population in terms of the distribution on those key variables like age and gender? That's where weights come in. Weight force the sample to look like the parent population. But that only matters if we are trying to make inferences from the sample to the parent population. If all I care about is saying, well, I just want to say 20% of my sample were smokers, I am not interested in saying 20% of the US population, then I don't need to worry about weight. So the bottom line of the story is that it depends on you. You as a researcher, you must know what you want to do, right? You can't ask another person and say, what do I want to do? I'm like, well, how am I supposed to know what you want to do? So you need to know what you are interested in doing. Am I interested in making inferences to the population, or am I just interested in just limiting inferences to my population, my sample? That is what determines whether you need to use weight or not use weight. So it starts with knowing what you have in your brain and what you're trying to do.
Thank you. Are there any other questions? Just appreciation. Great session, Prof. Very informative. All that's left now, okay, is for us to learn. Been an awesome 4 days. Thank you so much.
I have a question.
Okay. You can ask. The talker.
Okay, thank you. So I had put it on the chat box, but it seems you missed it. And the question is this. I know that when you want to use stata, or when you're using stata, a p-value of 0.000 is usually reported as p less than 0.001 or so. I want to know if it's a general thing to do, whether even if you're using any software, statistical software at all, when you get a p-value of 0.00, you have to report it as p less than 0.001 or so. Thank you.
Yes, you're correct. And the reason is because probabilities can range between 0 and 1, right? And so we don't want to report exact probabilities. So you can't report a probability like in terms of 0 and 1, right? When you say that the probability of this outcome is 0, that means there is no uncertainty in your answer at all, right? A probability of 0 is no longer a probability, it's a certainty, right? 0 and 1 are extreme. So the p-values ideally should range between 0 and 1, but should not include 0 and 1, because that means that this is no longer a probabilistic event. It is now a certainty that this thing is true. But we can't be so certain in science. And that's why when the p-value is reported as 0.00, which is 0, we report it as less than 0.0001 to still demonstrate that it's probabilistic, and to show that we are humble, and to show that we acknowledge that this is not a certainty. So yes, indeed, if the probability is given as 0, you report it as 0.01. And that's why on the chi-square platform, the chi-square platform is an interpreted software, meaning that it doesn't just report the results for you. It will take the results and then interpret them. For example, if the p-value is 0.000, it's not going to wait for you to report it accordingly. It's going to report it as the way it should be reported, so that even if you are not aware that that's the practice, then it does that automatically for you.
Thank you, Prof.
You're welcome.
Yeah, I have a question, please, Prof.
Sure.
Okay, thank you very much for the exciting lectures. I have a question around calculating or presenting the population count that we mentioned earlier.
Okay.
I know we said that it's interesting for one to present that aspect of the data because of policymakers. But I'm concerned, do we expect the population count calculated from the data to approximate the actual data, supposing the actual data exists. And because if you are presenting some of those data to policymakers, some of those policymakers may have those numbers, supposing those numbers exist. So, and so if you are calculating it from the data, will it actually be equal to the real data? And if it's not, that would then raise questions by policymakers as to how you are able to get those population counts. So that's the clarification I need. Thank you, sir.
That's a very good question. So first of all, that's why we round in survey analysis. We are very humble. We try to be very humble and aware of our limitations, right? So that's for one. That's why we don't present. Remember, if you remember, we're rounded to the nearest 10,000. That's the reason why. It would be very ridiculous for anyone to say, in the overall population, there were 112,256, 1,126,253 individuals. It's like, how did you know? Why are you so precise? you don't know that, so you can't be that precise, right? And so that's why we round to whatever, right? There's no rule that says you must round it this way. And that's why with weighted counts, you should also be aware that the results may differ from one paper to the other, depending on how they rounded, right? But in general, yes, these numbers are going to be very real. They may not match exactly, right? But they'll be very close to what they have. So yes, it will be pretty close.
Okay, thank you, sir.
Exactly. So that's why you also must be able to explain to the policymaker if he gets to, because the policymaker may have a number that, let's say they may have, instead of 1.12 million, they may have 1.5 million. And so they're like, oh, but you're telling me it's 1.1, but I have 1.5 million. You should be able to tell him that, well, sir, in this study population of middle and high school students, not every single high school type was eligible. For example, we did not include high school schools that, that are charter schools, or we did not include those that serve military schools. So it's possible that there are other kids that are in other schools that were not captured as part of the sampling frame. And in general, you should not even wait for somebody to explain or to tell you that before you ask, before you provide that information. If you look at the MMWR report, look at the best practice here. Let's see if I can find that report. Or have I closed it now? Okay, I think I may have closed the report, but let's just open it quickly. If you look at the MMWR report, you'll see the limitations here. Let's see. Second, these findings might not be generalizable to youth who are homeschooled, who have dropped out of school, who are in detention centers. Now, all are enrolled in alternative schools. What does that mean? Schools that were not part of a sampling frame for the NYTS methodology. There are a whole lot of schools. And that's why you also cannot take, this is also why you cannot, I cannot emphasize that enough, you cannot take the number like 19.0 and multiply by some census number and say, oh, this is the number of, no, you can't do that, because the census number is inclusive of all people who are in, who are in all types of schools, all schools. But the 19.0 number was not calculated among all those people. It was calculated among a very specific subset of schools. So you cannot take that number and then apply to that. That makes no sense, right? That's very, very biased. So that is why we cannot take the number. And this is a very, very common mistake made by researchers who are not familiar with methodology for complex surveys, right? They take the number here and then they go to the census and say, oh, the census says there are 6 million people here. So if I only multiply this number by that number, that will give me, no, that's not how we do it. You have to calculate it directly from the weights. And that's why the Calculus platform just gives, the platform makes it so easy for you. All you need to do is just check that box. All right, give me also the count. And it will calculate it for you accurately from the way it's supposed to be done.
Please, I have a question.
Yes, please go ahead.
Yeah, my question is on the training itself. Well, I'm already speaking to your organizer, the lady. But this morning I spoke to a number of people that I intend bringing them at a common platform for us to have a session like this. And then the doctors are asking, the physicians are asking. I'm actually calling from Ghana. The doctors are asking if the training, the certificate covers CPD point, and even if it covers for a fee, they are interested to consider. So I want to find out if it doesn't. Are you? Do you have any plans of organizing, because they are interested in the CPD points apart from the knowledge?
Okay, yeah, we can definitely arrange for CPD. Like, for example, we can have the courses evaluated by the Ghanaian Medical Association and evaluated as an approved for CPD points for your doctor, so that they can take it. So why not? And so that is definitely feasible.
All right, thank you very much.
Yeah. All right, Lungi Lazimu, we've answered all the questions.
Yes, sir.
All right, thank you so much. So please organize the office hours for the homework, and let's have folks attend, so that you can dazzle them with your statistical mastery. Thanks so much, everyone. Have a great
Can say
weekend.
no last question, please.
Oh, really? Okay.
Last question. Frederick. Oh, the textbook.
Oh, textbook. We're back to this textbook issue. Okay. Okay, I'll look for a good yeah, I'll look for a good field epidemiology textbook. That, unfortunately, honestly, there are not a lot of textbooks that really dive into issues of complex survey data from a very practical perspective in the field. That's always a challenge. Existing books that I know of are written by just career academics, and typically will present things from a very academic angle. But I'm going to take a look and see, and we'll see if I can share that. But yeah, off the top of my head, I can't think of any that comes to mind. But yeah, we'll look into that. All right, thanks so much.
Asking you to write one.
Oh, well, yeah, it's always hard to find time to do any writing, but yeah, that's a good idea too. All right, thanks everyone. Have a great weekend.
Thanks so much, Prof. We appreciate you.
Thank you very much, sir.
You're welcome.
Prof, thank you so much. We are grateful. God bless you, sir.
You're welcome.
God bless you, Prof. You are doing well.
Thank you, Prof.
All right, thanks everyone.
We appreciate it.
Enjoy your weekend.
All right, thanks.
Thank
you so much, Prof.
Thank you.
We appreciate you.
We will share the materials. We'll post them on our LinkedIn page. And please like our posts on our LinkedIn page.